Hi everyone, my name's Mason and I work for Comet Backup here in New Zealand. Welcome along. Today I'm just going to talk about backups, backup technology, how do we actually store backup data in our application, Comet Backup, why that's a good thing, the sort of challenges that you may face with different backup technologies, and I'm just going to talk about backups for a while. So let's start at the very beginning. Why do you need backups? Of course, everybody knows that house might burn down, laptop might get stolen, there's ransomware. There's a lot of reasons why you want to keep backup copies of things, and the most simple sort of way to keep a backup copy is to put it in a shoebox under your bed. So let's just start with not really a serious suggestion, but just for argument's sake, say we've got a shoebox under our bed and it's just got a copy of everything in it. This is a shoebox. I'm a software developer, not an artist, so it's a shoebox, and we all know time started in 1970. That's a programming joke. And so this is my shoebox full of all of my stuff, and it's fine. I know 1970 was a little while ago, and of course it's not everything, and I have more stuff that I want to keep, and I just next year I'll have another shoebox full of stuff, and this is my 1971 shoebox, and great. So I can just store stuff and keep a copy of it somewhere. I'm saying a shoebox here, metaphorical shoebox. This could be some sort of storage platform for your important data. My very important rocks and children's toys or whatever I had in 1970. So we've got the shoebox. We'll just have more and more shoeboxes, and there's several problems with this. The stack of shoeboxes just gets bigger and bigger, and I don't have that much room in the cupboard or under the bed to store all of these shoeboxes forever. So there's a few problems. So the first problem is the stack just keeps getting bigger. Now we can solve that by cataloging, sort of. There's various important things that I want to keep. For instance, there's maybe some holiday photos, a nice photo, nice sunny day on the photo, and maybe a hard drive image. I'm taking this into a little bit more real world now. Here's a hard drive that I want to keep. And of course, one interesting thing about photos is normally you take the photo and they don't really change that often. So this photo was taken in 1972. This is one of those little museum tags, imagine. That's sort of hanging off that. And then, of course, the disk image. This is my 1972 disk image. Of course, disks were smaller in 1972. It's maybe a bad example, but, imagine a whole disk image, something quite large. And of course, well, we've got a stack of shoeboxes. And now if we want, where are my holiday photos, I'll go straight to the catalog, pull them out, and then I don't have to sift through every single shoebox anymore. So that's fine, that's good. Of course, with a hard drive, the photo, you take the photo once, doesn't really change. The hard drive is changing all the time. Every time you take it back up, I'm just using round numbers for years here, but of course you should be backing up, daily or hourly or whatever. It doesn't really matter. But the point is we're going to have a lot of versions of this disk. We're going to have that version, and then we're going to have the 1973 version, and then we'll have another disk that's the 1974 version, and of course this just stacks up and it takes up a heap of space. Even with this cataloging system, we're still basically storing a ton of data for a very long time, and it's kind of frustrating because these disk images, they're 90% identical. I don't change every file on my hard drive every day. I know they're mostly the same. There's just little bits that change, and it takes us so moving on to generation 1 kind of idea, generation 2 kind of idea. Let's move on to generation 3, which is the realization that these files, they're mostly the same, and then the changes are just in little parts of these files. And I'm talking about disk images here as an example, but of course this also applies to databases and many other sort of concepts where you've got one big thing, a lot of little changes. Maybe it's a whole folder full of files, just a few of those files are changing, where you've got the larger whole and smaller changes within it. So the concept that I'm going to start with is just looking at the disk images. And one thing that people realize that you can do is you can store the disk image, and then you can just figure out the changes and store just the changes. And so I'm moving forward in time here. So this is the 1970, and this is 71, 72, 73, and so on. And I just look at the changes that took place in that time period, and I just store the changes. And this is kind of cool. It's got some interesting properties to it. It means that this just storing pretty much the minimal amount of data here. I'm storing the full image and then just the changes, and that's kind of it. There's a few problems with this model. One problem is this changes keeps getting longer and longer, and at some point, if I carry this forward to present day, 2023, if I want to restore today's version, there's an awful lot of history that I have to cope with. If I want to restore today's disk image, I have to restore the original one and then replay this change into it, 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 and eventually I will catch up to the current day. And the problem, it's kind of takes quite a long time to do all this replaying. There's also a big risk that if one of these things gets lost, take the shoebox analogy. These shoeboxes are getting cobwebby. There's just spiders, and this whole box is rotted, mildew, something. I've lost just this change, and now suddenly when I'm replaying things forward, I can't even really get past this part because you don't know how to make a coherent modern version anymore if part of the chain is missing. So it's a little bit risky to have these long chains. The risk is it's not that bad. You can manage the risk. The other problem is it just takes ages to restore because there's a huge amount of time involved in downloading every segment and reapplying them, huge amount of bandwidth to do a restore. Oh, wow, I had to restore 1970s data just to get today's data back, so that's a problem. So long chains are a problem. I'm just going to have a list of problems with this. One is long chains. Long chains are a problem. So one solution for long chains is just you periodically do a full re-upload. Instead of I'm going to take 1, 2, 3, 4, 5, and then I'm just going to do a whole new full re-upload, and that is fine, I guess. It means, and then from there on, I'll have more diffs going forward on that chain. This is kind of it definitely mitigates the problem of the chains being too long. However, we have a new problem of having to do this full re-upload, and suddenly, I'm talking about hard drive images that could be terabytes in size. It's quite bandwidth intensive to do this upload. So we want to avoid it if possible. It was quite nice just uploading the changes, but in order to mitigate the chains being too long, we want to have these full re-uploads, and that's kind of annoying. We don't want to do it. It's got downsides. So that's another thing is the full re-uploads. Full re-uploads. So that's problematic in its own way. So there's a way to get around the full re-uploads, which is to be a bit more clever. So maybe don't do a full re-upload, but think about the storage model here. So we've got this full image, we've got the changes, and if we actually applied these changes into this version, for instance, we'll end up with a synthetic 1971 backup where we've sort of merged that in and we've applied that diff. There's a few different ways you can do that. You can have coming from this direction, apply in changes and create these sort of synthetic full backups, or you can do it in reverse. You can always apply them and then create so this would become a 1971 backup, and then you can actually construct a reverse diff. And so what you end up with in this case is sort of the full backup moves along and it stays at the most recent date. And so you can very quickly restore the most recent version of the data, but then you have to replay these changes to go older and older and older. And most commonly, you're more likely to want to restore more recent data. So that's kind of interesting. The problem with all of these synthetic approaches is, so the synthetic approaches have got a problem. The problem is they require, computation. Actually merging this diff into the full image is a kind of computational process. It requires to be run on a CPU, and there's CPUs everywhere. That's not really a problem except for cheap cloud storage. We love cheap cloud storage. The AWS S3 compatible providers like Wasabi, Backblaze B2, iDrive. There's a lot of discount cloud storage providers out there with excellent reliability and performance, and they've really sort of enabled the industry to take off as it has. So, but with these sort of things, S3 compatible storage providers, you've just got storage. You don't really have a CPU to do the diffing work on, and so this whole model is just kind of untenable. And as well as that, there's the whole thing of you should probably be storing this diff encrypted and this diff encrypted. That means the CPU that does the work of merging it in has to decrypt it. That means where are your encryption keys? They're going to be on the cloud storage provider. Is that a problem? Maybe. So yeah, the problem with synthetic backups is if all you've got is cheap cloud storage, you have no CPU to do the work of diffing and merging. So the problem with synthetic is you can't really take best advantage of cheap cloud storage, which is something we all love cheap cloud storage. And there's another problem with the full re-uploads, which is the problem of retention models. So if you stick with the full re-uploads ideas, then you've got this issue where, say, I want to keep, you know, the last, say, 2 years worth of history, and my last 2 years of history eclipses past the last full re-upload. Well, if I really want to be able to restore from, you know, 1975's backup, in order to do it, I'm going to have to keep all of this extra unrelated stuff because it's sort of required in order to restore that. So you've got sort of amplification of your storage requirements for these full re-upload models. So we've got problems here, problems here, problems here, but really the sort of goal that we're all striving for is to be able to store just the changes incremental forever without a full re-upload. We want to be able to take advantage of cheap cloud storage. We want to have the whole thing end-to-end encrypted. And with this model, you just can't get there. And so at Comet, we have a completely different model, which works quite differently, and it has none of these problems. We can do incremental forever, no full re-uploads, encrypted client-side, all on cloud storage. And it's really cool. We use a technology called content-defined chunking that I will talk to you about now. To solve all the problems that we've been talking about, Comet Backup, our application, uses something called content-defined chunking, and it's a next-generation model compared to sort of the diff and full image that we've been talking about. In order to explain content-defined chunking, I'm going to start with an analogy. So imagine for a second that we're going on a road trip. And so this is my little car. Excuse my drawing skills. And so we're on this car and we're going on a road trip. I don't know if you guys go on road trips, but you know, nice fun road trip. We're going on a long drive to visit Grandma's house. Grandma's house is a long way away. And I don't know if you go on a lot of road trips or if you do this often, but it's if you have a car full of people, it's very important to have some sort of game to keep everyone busy. And the game that we're going to play on this road trip is we're going to stop at every stop sign at every bridge. We're going to stop at every bridge. There's a bridge here. There's a bridge here. A bridge here. A long bit without any bridges. A lot of bridges in a row. And then we make it to Grandma's house. And so it's fun, and the game that we play is every time on this car, every time that we see a bridge, we stop, we get out and we take a photo. Stop, we get out and we take a photo. This is us with our iPhone or whatever, taking a cool photo, looking backwards from where we came, just commemorate this fun road trip part. And we're taking this nice photo and we really enjoy it. And then eventually we get to Grandma's and we say, oh, look at all the nice photos we took. And so we've got this photo album. This is our photo album, and it's full of photos, nice photo looking back, and a sunny day. This fun. Oh, you can see the old bridge in the background, and so we've got this great big photo album full of photos. This is the album. But of course, we visit Grandma quite often. I don't know how often, maybe not every day, but maybe every day. We could visit Grandma every day, that's fine. Of course, Grandma tells us to be sun smart because in New Zealand we've got the ozone hole and we have to wear a hat when out taking photos. So, but every day, every time we do this trip, we take pretty much the same photos. And so on day one, we took, a lot of new photos, of course. And then on day two, when we did the trip, it's pretty much just the same photos. And it's nice to show Grandma the photos that we took, but we can just say, oh, here, Grandma, here's yesterday's photo. It's a little bit rude of us, but it's, we don't need to store these photos over and over again because they're pretty much the same photos. And pretty much every time we do this trip, it's the same photos, and we just get out at every bridge, take the photo looking back. The scenery hasn't changed, the landscape hasn't changed. Except one day something very exciting does happen, and something does change. Oh, there's a flood. This bridge has been washed out. And that's a problem. Luckily for us and luckily for Grandma, there is an alternative road available. We can take this road, and this road goes a different way and comes up and it connects up over here. And there's a different bridge. There's some different bridges along the way. And we get to stop out and take completely different photos. So we'll start off on our trip to Grandma's. We'll stand here and we'll take a photo looking back over this way. It's fine, it's one photo. We'll just get to the next bridge, take a photo looking back, and we get this photo. It's still the same photos. Here now we have to take the detour. We take a different photo for the first time. We take a different photo. We connect back up to the main road. This photo here is going to be different because we're still looking back at the way we came. But from here on out, it's going to be the same photos going forward. And so on, on day, day 10, we've got some the same, and we've got some new photos in the middle, and then it's the same again. And the key thing about this is this road is not really a road. Obviously, I'm talking about this road is actually your disk image or your database. And the interesting thing about stopping at every bridge is it doesn't matter if the road that we take is longer or shorter. It doesn't matter what changed along the way in each segment and each chunk of the road. We stop, look back, take a photo. The photos aren't really photos. They are hash validated sort of identifiers of the thing. And the bridges, the really important thing is that the bridges aren't really bridges. Of course, your database doesn't have bridges in it. What it does have is zeros of a polynomial function. And these are content defined, based on your database. We'll always find the same stopping points. And that's why it doesn't matter if, say this is a database and in the middle there's some database table and maybe more tables were added, tables were removed, big changes were made. We're always going to, all of that's clearly new data, new changes, but we'll eventually get back on track. We'll find the old data, we'll start taking the same photos, and then we'll only need to store them once in our picture book. And so the key properties of this content defined, this sort of segmenting or chunking is we can keep doing this forever. This is incremental forever. There's no need to ever do a full re-upload. We only ever upload the changes, the new photos. It's quite fast to restore because we can just say, oh, how do I get, day 10's version? Oh, it's this photo, this photo, this photo, this photo. Restore them all, done, that's it. So there's no need to replay all those changes like I was talking about replaying changes before. And we don't have the overhanging retention problem. We can just say, if I only want to keep the last week's worth of photos, these photos aren't referenced anymore, throw them out. These photos are still referenced, keep them. It's very easy. And so this is the model that we've chosen at Comet Backup, and it solves all of these problems that we were facing, and it enables these sort of key attributes. The key attributes that we're trying to achieve with the storage model, and that I think we have achieved, well, the first one is that it's incremental forever. And that means no full re-uploads. We can just always take more photos, take more segments, store those segments, and we never need to do any sort of full re-uploads to the data. Another key attribute is that it is compressed and encrypted. And this compression and encryption happens client-side on the device that's doing the backup. So the compression happens before it's uploaded, so we have a small amount of upload size. And the encryption also happens client-side before it's uploaded. So we've got end-to-end encryption. And that end-to-end encryption is actually really key for being able to take advantage of the next sort of key attribute here, which is just that compatibility with cheap cloud storage. So, if your storage vendor isn't trustworthy, well, you should pick a trustworthy one. But because all the data is client-side encrypted, there's no way that the cloud storage vendor is going to be able to see inside those individual chunk segments. So this provides sort of the end-to-end security of that customer's data. It's more compliant. It's easier for everyone. And so that's sort of key. And then there's one more attribute which I've sort of glossed over this whole time, which is deduplication. Now, all of these things are sort of in service of achieving small storage sizes, small amounts of upload, and deduplication is really a key aspect of achieving that. So when we see the same data, we just say, oh, we've seen that before, only store it once. It's really fantastic for space savings. That really goes hand in hand with that cheap cloud storage. Reduces your costs as a service provider if you have to store the data less often. And the deduplication with content-defined chunking works in a really interesting way because it applies not only, if we go on 2 different road trips and they go off on different paths, there's, some data is going to be the same, some data is going to be different. We store that only once together in the same storage vaults. So that's deduplication across sources, and it's also deduplication across time. So today's backup, yesterday's backup, the day before's backup, some things in common, some things that are different. Only store things once when we see them, and so that's deduplication. And that's really key for achieving those small storage sizes, incremental forever, no full re-uploads, And sort of, yeah, these are the key attributes of what Comet Backup achieves with content-defined chunking. That's all for today. Get started with your first backup in 15 minutes or less with a 30-day free trial from cometbackup.com.